Welcome back. So today we're going to talk about another special topic, sort of complementing the results we've been establishing in the course. In particular, we're going to talk about lower bounds. Let's recall our canonical training problem, where basically we are interested in minimizing the average loss over the training data. In particular, we have this empirical risk minimization problem, where again we assume that data comes from certain distribution P, which is most of the time unknown. Okay, and for this problem, we've talked about several efficient training algorithms. So we talk about stochastic gradient descent, of course, and we analyze its performance in different scenarios. We also talk about variations of a stochastic gradient descent, such as a stochastic gradient descent with momentum, debiased SGD with momentum, ADAM, etc. Okay, and when we establish theoretical guarantees for these methods, we basically establish upper bound on the performance of these methods. What's the worst convergence rate that that a specific algorithm could suffer for a specific class of loss functions? Okay, so that's basically what we talk about. What we didn't talk about, and we're going to talk about in this lecture, is basically the relevant question. So what's the fundamental limit of performance? Okay, what is the best rate achievable by any method that uses a stochastic gradient descent? That uses stochastic gradients. So it could be SGD, SGD with momentum, maybe SGD with momentum plus plus, like some algorithms we haven't talked about, right? So is there a way to combine the stochastic gradients in a maybe sophisticated way to get a better rate compared to the upper bounds we established before? Okay. So this is the kind of the question that we are posing here, and it is basically related to lower bound on performance as opposed to upper bound on performance. And we're going to try to basically study this question in a very, very basic setting. And my hope here is to sort of discuss the tools that are typically required to answer these type of questions, right? So, and for the most part, I would say these tools could be used not only to study lower bounds in different optimization settings, stochastic optimization settings, but in other statistical decision-making problems. Okay. For us, however, we're going to, as I mentioned, focus on a simple case. In particular, we're going to assume the case where the distribution is unknown, so naturally it's unknown, but we're going to restrict our derivations to the simple case where the loss function is convex and G Lipschitz. Okay, so what's the setup? As we're going to see, the setup is that we are going to observe a sequence of stochastic gradients. So these are our observations, and based on these observations, we are producing, let's say, a solution. Okay, it could be produced by using SGD or any other method. And the idea is that we want to understand what's the performance of this method in the and what's the fundamental limit of performance of the solution produced in this specific way. Okay, so let's first recall the upper bound we established for SGD in this case. So we said that for SGD that utilizes these stochastic gradients in a specific way where we update the parameters using our simple update. As long as the data are IID and generated from this distribution P, we'd be able to establish an upper bound on the expected performance. Okay, so the expected suboptimality gap was bounded by basically how far we are from the initialization. So this is what we called D, if you recall. And then the Lipschitz constant plus the variance of the stochastic oracle divided by a square root of T, where the expectation basically is with respect to the source of randomness, right, in the process. In particular, that source of randomness is basically the joint distribution between among the observations. Okay, the joint distribution of observations G1 through GC, and I'm going to denote that distribution with P PT. Okay. Right, so this is the upper bound we establish, and as we're going to see for this setting, we can establish a matching lower bound. So what does that mean? It means that SGD will be an optimal algorithm for this case in the worst case. So in the worst case, there is no other way to combine the stochastic gradients to get a better algorithms. But naturally, practice is sometimes more has a structure, so it's not as basically as ugly, if you will, as the worst case. So we will be able to get better rates using potentially different algorithms. Okay, all right. So nonetheless, our question about lower bound basically is about studying how good the suboptimality gap is going to be. Okay, and this obviously depends on distribution P, right? So that the data is coming from, which is unknown. Okay. So we cannot take this gap as is, this expected suboptimal gap as is, as our notion of risk to minimize it. Okay, so to get a lower bound, because it depends on this unknown parameter P, and therefore in scenarios like this, when there is this unknown quantity, when you want to talk about optimality and lower bounds, you typically need to impose additional criteria. Okay, so in general, we require additional criteria. In particular, one criteria that is very important in the statistical decision theory literature is the min-max risk. Okay, and this is what we're going to leverage for our purpose as well. So what's the min-max risk? So it's basically it's saying the risk. So we are interested in the solution that achieves the smallest maximum risk among all alternative distributions that belong to some set D. Okay, so it says that if P comes from, let's say, a set of distributions, maybe there are 2 distributions, right? So what's the worst expected suboptimality gap that my solution is going to suffer from? Okay, so in particular, the minimax risk for us is going to be written as follows. So again, let PT be the joint distribution of observations. Okay, then the risk that we are interested in is basically the worst case expected suboptimality gap over the set of all alternatives, which we denoted by D. So the maximum over the distribution, the maximum expected risk, where basically again we define this expectation with respect to the joint distribution of observations that are generated from this distribution P that we are selecting from set D. Okay, and then the minimax risk of a solution or a minimax optimal solution would be the solution that minimizes this notion of risk. Okay, so that's why we call it minimax, because we have a minimum here. We are interested in minimizing the risk, and we are talking about the worst case risk by taking this maximum. So any solution that achieves this the lowest risk according to this criterion is called the minimax risk. Okay, and if you establish a lower bound on this risk, therefore you are establishing a minimax lower bound. Okay, and in this lecture, as we're going to talk about, we're going to establish a minimax lower bound that matches precisely the upper bound that we have here for SGD. All right, so what is our strategy? Our strategy is that, again, we want to lower bound the risk that we just defined, and we're going to do that step by step by constructing a hard example. So essentially the idea is that we're going to construct a set of distributions and a specific loss function such that it is not too easy for any optimization algorithm that uses a stochastic gradient descent, a stochastic gradients to lower the risk. Okay, so many times when you want to establish lower bounds, you have to come up with a hard example. Right? So that, hey, this is a hard example, so not only SGD but any other algorithm cannot crack this as efficiently as we want. Okay? So that's why I would say many times establishing lower bounds could be difficult, because coming up with these hard examples in different scenarios could be non-trivial. Okay. Right. So our strategy, again, lower bound the risk step by step by coming up with the hard example. In particular, for this hard example, what we're going to do, we're going to reduce the optimization to a statistical decision-making problem. And this is called basically a hypothesis test or hypothesis testing problem. So as I said, the idea is that we have two distributions, right, that are different but very similar, and it is going to be very difficult for us to determine from the observations, from the stochastic gradients, which distribution is basically generating the stochastic gradients. So that basically means that because it is very hard for us to test this binary choice, we're not going to be able to get a very fast rate, let's say, on optimizing the functions. Okay, and to achieve this, we're going to use tools from information theory. So there are different elegant techniques in terms of establishing lower bounds. So Lecombe's method, Fano's inequality, and Nasud's method, hopefully I'm pronouncing these names correctly, are canonical tools to establish these kind of results. Our construction and derivations is going to follow the celebrated Lecombe's approach, basically, Lecombe's method. Okay. All right. So what we're going to do, therefore, we're going to come up with a construction, and without loss of generality, we're going to assume that the set of distribution D is a finite set, and in particular, we only consider two distributions. Okay, so the stochastic gradients could come, or the distribution of the data could be either P1 or P minus 1. We don't know that, and we are interested in bounding the expected suboptimality gap in the worst case. Okay, so we are kind of making an assumption that there is a distribution over this set D, okay, so that we can use to sample either one of these data distributions, okay, and we're going to make an assumption here, and that this distribution is basically uniform. So it means that the data distribution could be P1 or P minus 1 with equal probability, okay. So this is basically part of our construction. All right. So why is this useful? Why introducing this probability distribution is useful? Well, we can trivially establish our first lower bound on the risk. So for any W, we define the risk to be basically the worst expected suboptimality gap over the set of all alternative data distributions. Okay, so this was basically the definition of risk. Now, given that maximum is larger than average, okay, so very, very trivial statement, we can lower bound this risk with basically by replacing the maximum with an expectation. Okay, so we are saying the maximum is basically larger than average. So we do this replacement, we trivially get a lower bound on the risk. Now, what is this expectation? So what is this expectation of the expected suboptimality gap? It's basically saying that it's going to be the suboptimality gap according to P1 times the probability that P1 is a data distribution plus the expected suboptimality gap according to P minus 1 if P minus 1 was the underlying data distribution. Okay, and as always, PTI is basically the joint distribution of observations, stochastic gradients, when again the underlying data distribution is PI. All right, so this is basically our first step towards lower bounding the risk, and also as part of doing so, we sort of limited ourselves to this simple case where we have only two data distributions that could be equally distributed or equally selected. All right. Now this is a place that we want to basically start transitioning our problem to a statistical decision-making problem, or in particular a binary hypothesis testing problem. Okay. So in particular, we're going to construct a test based on the optimization performance. So what do I mean by that? I mean that essentially we're going to decide which underlying, which P was the underlying data distribution. Was it P1 or was it P minus 1? How can we make this decision? Well, the only observation that we have access to are the stochastic gradients, G1 through G capital T. Based on these observations, we want to make a determination. What can we do? Well, based on these observations, these stochastic gradients, we can try to perform optimization. Okay? And then we can use the optimization performance to see or to decide which data distribution was selected. If the performance was low, let's say on one of the loss functions, then we say that, okay, the first data distribution was the true one. If on the other hand, the performance was low, or the suboptimality gap was low on the second loss function, we would say that the second distribution, P minus 1, is indeed the underlying data distribution. Okay. So again, in hypothesis testing, the goal is to determine which of the two alternatives is correct based on our observation. In particular, the setup is that there is someone, for instance, nature, that chooses a data distribution, and as a result, we're going to have a loss function, a stochastic loss function. And as I mentioned, in our case, the nature can only choose from a set of two alternatives. Based on this choice, naturally, we observe some stochastic gradients for this loss function. Okay, and the goal, as I mentioned, is to correctly identify the choice made by the nature. In particular, by that I mean, from these stochastic gradients, we want to decide which distribution or loss was chosen. Okay. Now, here's the idea. The idea is that this task is non-trivial. It means that the probability of making a mistake is lower bounding, meaning that it is non-zero. Okay, and the idea is that as we're going to see, we typically make or construct examples such that the data distributions P1 and P minus 1, and as a result, the loss functions are different, but very, very similar. So therefore, it is difficult for us to determine which data distribution or loss function is the true one by merely looking at the observations. So therefore, we can leverage that construction to lower bound the probability of error, and the implication for us will be that there will be a lower bound on the convergence rate of any algorithm that uses stochastic gradients to optimize functions. So with that, let us continue in the next part of this lecture, where we're going to talk a little bit more about our specific construction, in particular the data distributions, as well as the resultant loss functions. I'll see you next time.